Why is a door easy to open at the handle, but stubborn near the hinges? The answer is torque, the part of a force that produces rotation. In this lesson, we will turn everyday spinning into a toolkit you can calculate. Torque depends on three things: the force, the distance from the rotation axis, and the angle at which the force acts. For a force of magnitude, F, at position R, the torque magnitude is tau equals Rf sine theta. The most useful special case is a perpendicular push. Then sine theta equals 1, so torque is simply force times lever arm. A 10-Newton push applied 0.8 meters from a hinge produces 8 Newton meters of torque. That same principle explains a wrench and a seesaw. A longer wrench gives the same force more leverage. On a balanced seesaw, clockwise torque matches counterclockwise torque, so mass times gravity times distance is equal on both sides. Torque is the rotational counterpart of force. Net force changes linear velocity through acceleration. Net torque changes angular velocity through angular acceleration. For a rigid object about a fixed axis, the relationship is net torque equals moment of inertia times angular acceleration. Moment of inertia, I, measures how strongly an object resists changes in rotation. It depends not only on how much mass the object has, but where that mass sits. Mass farther from the axis contributes more because distance is squared. A solid disk and a thin hoop can have the same mass and radius, yet the hoop has the larger moment of inertia because more of its mass is farther from the axis. The distribution of mass matters as much as the total mass. Now consider an ice skater already spinning. When the skater pulls their arms inward, the mass moves closer to the axis, so moment of inertia decreases. If external torque is negligible, angular momentum stays constant, and angular speed increases. Angular momentum is the rotational analog of linear momentum. For a rigid body rotating about a fixed axis, L equals I omega. More generally, angular momentum is a vector, and its direction follows the right-hand rule. External torque changes angular momentum over time. Torque also connects to rotational work and energy. A torque acting through an angular displacement does work, and a rotating rigid body has rotational kinetic energy, 1/2 I omega squared. Do not confuse that energy with torque. They play different roles. When solving a rotation problem, start by choosing the axis. Draw every relevant force, find each lever arm, assign a sign to clockwise and counterclockwise torque, and add the torques. Then use net torque equals I alpha, checking units and limiting cases. So the physics of spinning is one connected story. Lever arms create torque, torque creates angular acceleration, mass distribution creates rotational inertia, and angular momentum explains why a skater speeds up. In the final lesson, we will see where prediction breaks down in chaos.